speaker is David Abrahams, who does not need any introduction.
And give one anyway if you want.
Yes, and I hope David will be running similar program in a few years, reporting the progress in the area.
Thank you very much. Thanks, Gennady. Thank you to you and Anastasia for a wonderful conference. It's so good to be with so many friends and colleagues. And thanks for the dinner last night, wonderful. And Lasha, thank you to your wife for a wonderful concert yesterday. For those who didn't make it, you missed a treat. It was wonderful. Thank you very much. So I'm going to talk about this subject here that I know nothing about. And you notice I acknowledge at the bottom several people. Mike's there and Malta's there and Luke and Fabienne. So I had the privilege of, at the program, multiple wave sketching program last year, I had the privilege of inviting myself to give a couple of lectures earlier this year, have a bit of winter sunshine in Australia and New Zealand, thanks to Luke and Fabienne. And a big part of the Waves community's research activity down under are ice problems because of, for obvious reasons, with global warming. And they talked about one physical phenomenon, which I'm going to talk about today. My idea about edge waves existing on these ice shelves. I'm going to talk about what ice shelves are. So very gentle introduction for the first half of the talk to hopefully wake you up. And then I will do a bit of Wiener-Hopfery the second half. And so there's two questions here. Mathematically, is there a solution of my problem? And is that solution of physical relevance? So there's two questions. Almost certainly no to the first, I suspect, but I want to prove you that the answer is in the affirmative for the first question. Okay, so let's talk some physics. Sea ice, and it's a really huge thing. So I've just nicked these from various websites. So if you look here, every year as the sea cools down in the winter, so in the summer months for us, in the winter in the Antarctic, the sea ice, so the sea freezes because of the temperatures and forms a very, very large sheet. And I'll show you some satellite pictures in a second. And it's so vast, it covers about 4% of the Earth's surface around Antarctica. And then sea ice forms around lots of other areas in Canada and other regions in the northern hemisphere as well as the summer. And then in the summer it melts and it contracts to a much smaller area. But what's been noticed in the last few years is that freezing, thawing, melting cycle is receding. And so sea ice is becoming less, and the type of sea ice is more broken up, and you have these various types of ice like pancake ice, which you'll see has different properties which may be of consequence. So last year, the last 3 years, it's in the summer months, it's down to under 2 million square kilometers. So it's happening elsewhere. What's the issue? Is it a big issue? Do we need to worry about it? Well, yes, it is. So these are some pictures that I've just nicked. February 24th last year, and that's the summer. And you can see the sea ice is around, so this is sea ice here, and just little fluffy bits around the edge of Antarctic. And this is Antarctica, and of course there's always a problem with Antarctica. Which way up is it? Do you normally draw it? So the British own or occupy this territory here, so that's normally the way we draw that up on our maps, as you'll see in a minute. Okay, and then this is from the winter, and you can see now that little bit sticking out, this peninsula here, was sort of over here in the last picture, but the sea ice has formed all around here. It's vast, so it's huge. And in some sense, because you've got the Southern Ocean all around here, which is basically an uninterrupted ocean, so you have very, very large tidal currents, or currents due to the rotation of the Earth, massive volumes of water, huge amounts of energy. And that causes lots of swell and activity, and then storms form off this region and impact on the ice in the vicinity. So this is a picture from a paper I've been involved in, showing the British bit of the Antarctic, and we have Rothera, Halley and Sky Blue, 3 sites where we have bases. And there's an issue. Halley, if you look at it, it looks like some sort of caterpillar, if you've seen pictures. And it's designed, it's on legs, and it's designed that it can actually drop its legs, be transported on wheels, and trundle away because it's on the ice shelf. And if the ice shelf gets a bit thin, it can move. But there's been such a loss of ice shelf on this region that they know it's doomed. And eventually Halley will break off and float away, never to be seen again. Okay, and these things are meteorite collection zone, which is a talk for another day. Okay, so this is what ice shelf looks like, and this is what sea ice looks like. So this is sea ice, it's thin, and it's formed of brine water, it's sea water, so it's salty, whereas that is the runoff from glaciers that have formed on the Antarctic and are flowing towards the sea. So they're completely different. One is formed on land and flows out to sea, and the other is formed cyclically as it cools, the water freezes and then thaws in the summer. Okay, so Luke and others have been working on these problems of the effects of receding sea ice and its impact on ice shelves. So I'll draw a picture of cross-sectional schematic of what an ice shelf looks like in a minute. But essentially what they say, sea ice acts as a buffer to protect ice shelves by damping destructive ocean swells before they reach the ice shelf edge. Okay, but where there's regional loss of sea ice, storm-generated ocean swells can readily reach the exposed ice shelf and cause its outer few kilometers to sort of move, and that flexing and internal strains starts working the cracks, the fractures that are naturally there, and then it forms a greater carving of icebergs off the front edge. And this is worse than just losing ice shelf, is the fact that these carving removes these keystone blocks. The idea is it's holding back the glacier, which is under enormous pressure flowing down to the sea. And if you remove that, then suddenly there can be catastrophic movement of the glacial ice, and you have a large breakup, and then the shelf can virtually destroy itself, as has happened a few times. So you can get runaway collapse. And of course, we know that you're putting a load of glacial ice into the water, which then melts and it raises sea levels around the world. So this is the big issue affecting us. Sea level rise is unstoppable with this present rate of loss of ice, glacial ice or land-based ice as it flows into the sea and melts. Okay. So here's a schematic of what happens. So the glacial flow, it snows, the snow gets compacted in the center of Antarctic, and then naturally under gravity it flows. It gets stuck at the mountain ranges because there's some very large mountain range underneath the Antarctic, but where it can get round it, it flows into the sea. And if I go back a couple of slides, you can see here, I should have shown you, that is actually sea under there. So this is the land around here. And so the glacial flow has been coming down from these regions, and the ice just floats on the water. And so this forms this enormous shelf. These are hundreds of kilometers wide. So it's massive scale. And so if this starts cracking and loose, that's a huge amount of ice, which then goes off into the further north. Okay, so here's a schematic. The glacial flow reaches the coastline and the sea, the ocean, and then the ice is lighter than water, so it floats on the water. Okay, and it forms this large shelf. And this could be hundreds of meters deep, if not kilometers. And then you have this sea ice forming. And so in the winter months where the activity is its most violent, the waves can propagate along and they try and reach the ice shelf. But because of this sea ice, the idea is it attenuates the waves. So the major impact of all that energy from the swell, from the waves, is reduced by the time, and it protects the ice shelf. So that's the idea. Okay, so Luke and others in this room have been looking at this problem where you have the breakup of that sea ice, the waves can penetrate further, and then that flexes the ice shelf itself and can cause an increased rate of carving of icebergs. And they have analysed this in terms of looking at the waves propagating along this incident, just sort of normally to the edge of the ice shelf. Okay, so they're thinking of waves coming in here and then exciting this thick ice shelf, which can be thought of as a thin plate if you're thinking of very, very long wavelength waves. Okay, so that's the dynamic. But it got me thinking that, well, before I say that, this is a collapse that happened. So this is in one of Luke's papers. I hope he doesn't mind me borrowing it. And there was a very rapid event where they lost a lot of ice at the front of the ice shelf. And then this was within a few weeks. This picture turned into this picture. So it caused, we were talking about those keystone blocks broke away, and that released the pressure, and then all of this started cracking. It lost an enormous amount of ice shelf in just a few weeks, which is catastrophic and adds to a huge amount of ice which will eventually melt. Okay. And that's a picture of carving which you've seen in the ocean. So these are very, very large, as I say, and they carve off. Okay, so my hypothesis is we know that on thin plates that you can have not just waves that impinge normally to the surface, so treat it as a two-dimensional problem, you know, waves coming in and reflecting and transmitted. But what about the existence of edge waves, which we know in thin plates or in any place, a full 3D elastic plate, if you look at it, you can compute the solution that you can get waves which run along the edge of the surface if you have a free edge here, and it decays exponentially into the ice surface itself. And the reason why these might be important is because they're localized, they constrain the energy. There's certain frequencies or wave numbers for which these persist according to the material parameters. As far as I know, no one has thought about this problem where you have seawater here and an ice shelf there. And so you would think that the seawater allows surface waves to reflect, so the energy propagates out into the sea. If you just look at this in isolation, in vacuum, then there's nowhere for the energy to go. But it doesn't mean that you can support these edge waves. So do edge waves exist on these ice sheets? So we'll take an incredibly simple model, of course, and then do something about it. And then the semi-infinite nature of this problem makes it amenable to Wiener-Hopf analysis. So this is my talk. Let's write down the boundary value problem, and I want to do some non-dimensionalization. I think it's important to get the non-dimensionalization right for the problem, otherwise you can get confused. Then I'm going to go back and let's do some really simple theory. Let's look at a one-dimensional plate. So forget about edge waves. So there's no propagation along the plate. Just look normal to the free edge, and then add in a fluid and see what happens. And we know you can get fluid-coupled plate waves. But let's just go through this exercise. Then we'll look at plate edge waves in vacuo. So this is the Kanenkov solution, or there's numerous authors who believe they've found this edge wave solution. And Andy Norris and I have written some work which shows there's about 6 authors who've invented or discovered plate edge waves. But we believe Kanenkov solution is the most elegant and probably the oldest. I doubt if I'll have time to do anything about an eigenvalue problem. But if you think about it, I'm not looking at forcing, I'm looking at an edge wave that's not forced, it exists. So therefore it's an eigenvalue problem. So there's no forcing in my Wiener-Hopf problem. I need to find solutions of some sort of eigenvalue Wiener-Hopf problem. And then I'm going to go through that problem, this incredibly simplified problem, but it still looks a bit horrendous in my handwriting. And then I'll make a few conclusions. So let's do that. Okay. So first I'll define the problem and then I'll come back to it later on. So thin elastic plate sitting on top of incompressible inviscid water, free surface water, so no capillary waves, surface tension, just gravity waves, okay? Infinite extent in Y and semi-infinite in X, and the fluid occupies Z less than 0. The hats mean they're dimensional variables, okay? And so this is in cross-section, and I keep in Y, which is sticking out of the board or into the board. And I have a elastic plate equation, linearized thin, the simplest plate equation. But we proved that this works for Mindlin plates or whatever. It's a generic phenomenon. It's not special to any particular plate theory. D is your bending stiffness. This is the Laplacian operator squared. It's fourth order, the bending moment. And then this is the inertia term. So rho P is the plate density, H is the thickness, and P is the pressure imposed on the plate due to the water pressing on it from below. Okay, so I'm assuming the pressure is 0 above. You can just get rid of it. This is your free surface boundary condition. So that's gravity, and this is the vertical velocity. And then we've got Laplace's equation in this fluid. And it's really nice. Looking at these eigenvalue problems are wonderful because we know the solution must go to 0 for W, the plate deflection as we go off X bigger than 0, and then down here in any direction phi must go to 0. So although this allows waves to propagate, if we're looking for localized modes, then the field must decay exponentially as X goes negative for the velocity potential. Okay, and then we need some edge conditions on this plate. So we know if it were a second order equation, we need one boundary condition at one end and one at the other. And we know we have some outgoing condition or decay condition at infinity here. So that will take care of two boundary conditions. So we need two more because it's fourth order. And these are the free edge conditions. Mike wrote down the same yesterday, but without a y component. So it's the second derivative. So it's the force and moments are 0. But because you have y dependence, then Poisson's ratio gives you a coupling between the two. Okay, so that's the setup. It looks quite messy, but for all of you who've worked with these problems, it's very simple. G is gravity, D bending stiffness, plate thickness, Poisson's ratio, Young's modulus, fluid density, plate density. And we know for ice and water, then the densities are somewhat comparable. So we can't make any simplifying assumptions. Okay, the non-dimensionalization I like to use is to scale on this parameter mu, which is the sort of plate properties. So I can get rid of the fluid if I want to, and then this still persists. But it depends on the frequency. So what I'm going to do is I'm assuming some monochromatic wave, so there's just a single frequency omega. And that will be part of the eigenvalue problem implicitly later on. So omega's hidden in there, and then I've got the scalings to get the dimensions of phi and w right here, and then mu is a 1 over length, so it depends on those parameters there. And that simplifies the plate equation. It just is this operator here acting on w minus w, so I've scaled out the inertia term here. And then my fluid loading parameter comes in here as a tau, and I have an I because of the phase factor. So tau is this parameter, which is like the ratio of the densities of the fluid and plate, the plate thickness, and this length scale mu. Okay. So it cleans the problem up a bit, and let's go. Okay, let's do some very simple flexural waves. So 1D plane flexural wave. If we get rid of the fluid, I just set tau equals 0, so the density of the fluid goes to 0. I just have this simple plate equation. We know that has 4 solutions, plus psi 1 and minus 1 and plus and minus I. Okay, so this equation allows flexural waves. So the psi equals 1 is a flexural wave traveling to the right. and -1 to the left because of my definition of time that I put in there. Okay, so we all know flexural waves, thin plate theory gives the lowest Lamb mode antisymmetric solution of the 3D elastodynamic bar. So this is good. And then if you add a fluid on top or below, let's take it below as we had before, and let's make it compressible. So I've got Helmholtz's equation instead of Laplace's equation. Then we can modify this solution, or we plug that same solution in and we look for phi solutions, and then we get this form. It decays exponentially in Z. Z is measured negatively, so this is a plus. And then we have this phase relation here between W and phi. And the psi is modified now by the presence of the fluid, and your plate equation for the roots for psi is this square root psi squared minus kf squared. This psi to the 4th minus 1 equals tau. And so you can easily see that this has one and only one real positive solution by plotting the left-hand side and the right-hand side. Sorry, I've divided through by this parameter. So the intersection of these points gives you this solution. So you add a fluid, it can be a compressible fluid, to your plate wave solution. It modifies the wave number, but it still persists. So, and so it allows fluid-coupled plate waves to propagate, which we all know. Okay, that sounds sensible. But what about waves propagating along the edge of a thin plate? And that includes then dealing with the free edge conditions. So we have to satisfy this plate equation here. Again, I'm doing it in vacuo now, so let tau be 0. And then I'm introducing these free edge conditions, which have to be satisfied for solutions of this form. And I've not got anything else, as I say, in the problem, except I've taken an e to the iky solution out, a sort of plane wave solution propagating in the y direction, to reduce it to a problem just in x. And so I can try plugging in a solution of the form I want, which is, I'm now looking for a solution which is localized to the edge, x equals 0. So I'm looking for a solution which decays away from the edge. So I plug in an ansatz or solution of this form, and that gives me this relationship, which says that psi is plus or minus root k squared plus or minus 1. So 2 roots of that. And I want both of those roots to be real so that I have this exponential decay. So then k must be greater than 1. So I'm looking for a subsonic wave less than the wave speed for flexural waves in the plate. And so it can be those solutions. And then I'd take a combination of those 2 solutions. You need both of them together. And then they have to have appropriate weightings in front of both of these terms in order to satisfy these conditions. And I've just, to make things quicker, I've introduced these weightings, these constants in this way, so that it satisfies the first of these edge conditions. And we'll see that that does that automatically. And then the second one, to get it, will give me some relationship on k. So it solves for k. So this is the Konenkov ansatz. And of course it's linear, so I could have any multiple of this solution. If I plug it into the first equation, then the nature of it, this is the same as that. So it gets 0 because of the form of those coefficients I chose. And the second one gives me these 2 terms, which I can rearrange to give me that, or I can rearrange into this form. And this is the Konenkov form that people write down. So k satisfies this relationship here, and it's so simple that you can actually multiply it out, square it up, solve, and it gives you this. K depends only on Poisson's ratio for this, because there's no other parameter in the problem, and it's this. And it's pretty close to 1, but slightly bigger than 1. So it really is similar to a Rayleigh wave on the edge of a wave, but this is a simpler situation. But the free edge condition allows these solutions to exist. If you take clamp conditions, you can't get any edge wave solutions. So these solutions exist, they propagate without attenuation along the edge of the plate. let's go back to the problem I want to solve now. So I've got 15 minutes or so to do that. Oh no, 20, yeah, 15 if I want to stop. Okay, let's try and do it then. It's very messy and I apologize for that. And I won't go through to the full solution. I just want to get through to the point of the punchline of how you prove that these things exist. Okay. And there's various ways of doing this. And I wrote a paper with Andy Norris in 2000 on a related problem to this. And I think this is a simpler way of doing it than is shown in that paper. So we have the free edge boundary conditions at x equals 0 for the displacement. We have the thin plate equation in this dimensionless form, and W is related to the velocity potential through this simple relationship. Now my water wave free surface condition is the normal one of the vertical velocity minus k times. The potential is 0. We've got Laplace's equation, but now I've introduced this e to the iky term, which I've taken off Laplace's equation, and it gives me, so this is a modified Helmholtz equation. So this is nice, because it's going to try and make things go to 0 at infinity, which is good. And as I said before, W must go to 0 as x goes to infinity. The parameters I've got in here are the free surface dimensionless wave number, this parameter here. I've got the fluid loading parameter tau, the edge wave dimensionless wave number, which is the thing I'm trying to solve, just like for Konenkov's solution. And then I've got Poisson's ratio floating around in there. And these, so we've got 4 parameters to tweak to try and find. So we've got quite a number of unknowns, of things that we can actually pick from the physics to allow us to find something. But I also should say that K and tau are frequency dependent dimensionless variables. So we can define a parameter which is frequency independent by taking this ratio of tau and K together. I won't use that in this, but it's useful to sort of see that. Okay. So I want to solve this problem. How do I do it? Okay. So Wiener-Hopf free. Field decays to 0 at infinity. So brilliant. All my Fourier transforms are just going to exist. I don't need to worry. If I can't find a solution, then it will be big or something will happen at infinity, which I need to take into account, but that will mean I don't have an edge wave. So if I can find one, then it definitely satisfies this. So that's great. Field is well behaved near the origin due to the plate. The plate constrains the field in phi as well as for W. So if you do a local analysis, you don't get the same problems that you have if you have a mixed Wiener-Hopf problem where you have square root or other more complicated behavior locally, but this is smooth. It's constant plus x or z and other terms, and only the non-integer powers come in later on, quite a long way down. So this is pretty smooth near the origin. So that's good as well. So what we know in our transformed plane, what the behavior like at infinity in this alpha plane, okay? So we'll take the Fourier transform in the usual way, plus I alpha x, half-range transforms in the usual way. The z subscript means I'm taking a Fourier transform of the derivative of phi, and the inverse is the usual thing. And now, I know I like to have indented strips contours, but I don't need to here. My contour by definition, if I'm looking for a localized solution which is bounded, will have no singularities on the real line. There'll be no wavy terms going to infinity. So I can't have any singularities. I must have a proper strip. I'm going to have plus or minus ik floating around, so there's a branch cut going to appear. Is that the width of my strip or is it narrower? It doesn't matter. All I know is I've got a well-defined strip if everything works out okay. So this is wonderful. It's as easy as it gets, except that there's a lot of stuff to do and there's lots of parameters. Okay, so the governing equation, if you differentiate it, if you take a Fourier transform, is that, as we know. We're looking for solutions which decay as z goes to minus infinity, and I introduce this gamma, which is my square root function, but that's got branch points at plus or minus ik for k real, which is what I'm looking for. So this is the usual form of a solution which is bounded, but a of alpha is an unknown. It's the thing I want to find in the problem, okay? And then I can split phi up into its plus function plus its minus function, and that's equal to a, and the derivative of phi is phi z plus plus phi z minus, which I can get from just differentiating this, gamma a, z equals 0, so I get gamma a is this thing. Now I can use these to write the boundary conditions when I Fourier transform them into this function which is dependent on a. So the free surface condition is just on the x less than 0, so it's phi z minus minus k, phi minus is 0. And so I know that that's equal to 0, so if I take the whole Fourier transform of that quantity, even though I don't know it on the x positive, this is some unknown plus function. It's unknown, and I call that psi plus, and it's in terms of a by this relationship here. And we know that psi plus, as they go to infinity, because that's related to the phi at the origin, it goes like a constant, so it's 1 over alpha behavior. Okay, now the half-range transform for the plate equation. So what I do is I just hit my plate equation with the Fourier half-range Fourier operator, stick it through, and then I have to integrate this by parts. The behavior at infinity is 0, so it gives me no contribution, but at x equals 0, it gives me some polynomial terms in alpha, plus these unknowns when I've used the free edge conditions. So I get this equation. So integrating by parts relates this down to a relation between phi z plus and phi plus, and then I've got this stuff here equals a polynomial, and w naught, wx naught are the displacement at the origin and the derivative, the slope at the derivative, which I don't know. So they're unknowns in my problem. So I'm introducing this, and I've got two unknowns. I've applied the edge condition, so those unknowns must come out in this. We know what they will give me. Okay, so this thing here, I can write now, this is equal to 0, so if I do the whole Fourier transform of that thing across the whole x on z equals 0, then I get this contribution from this is equal to q, and then psi minus, and then I can relate it to a just by simply plugging what I know for a into here, and I get this equation. So this says psi minus is equal to this psi z minus minus 2 phi minus. Okay, but we know a from what I did on the last slide is equal to psi plus over gamma minus k. So I can eliminate a in this, and I could get that equation. So I've got my Wiener-Hopf equation. So it's very simple, standard stuff. And so I want to solve that, okay? I don't need to solve it all to get whether I've got edge waves or not. I just need to do enough. So what I've got down to is I've got an unknown minus function and an unknown plus function, and I know something about the behavior at infinity of both of those quantities, and this is my thing I have to factorize. I'm calling this stuff m, and so I have to factorize it. What I know about m is that for large values, it goes like alpha to the 4th times gamma, which is mod alpha, over gamma for large alpha, so they cancel through, so it goes like alpha to the 4th. So also this is symmetric in alpha, so m plus of alpha is equal to m minus of minus alpha, so I can relate the two. So both m plus and m minus must go like alpha squared. So that Wiener-Hopf equation can be rearranged into the standard form, get the m minus here, m plus here, and then this goes like order alpha, and this goes like order alpha. So extended form of Liouville's theorem, that's equal to c alpha And I put an I in there, in that coefficient, for a reason. It'll become clear in a second. So I've got another two unknowns. So I've got W0, WX0, C and B in this problem, 4 unknowns, and it's a bit mysterious. I've already applied the edge condition. So how am I going to solve those? So the way you solve them is to say, well, I've defined my psi plus and psi minus as plus and minus functions, but when I actually write their solution down by just taking this equal to that or this equal to that, so if you take these two, it's just equal to this thing, and that gives me A, but this psi plus must be a plus function, and similarly psi minus must be a plus function. In particular, when I rewrite in terms of my fundamental variables, phi z plus and phi plus, then these also must have no singularities. This is a minus function, so this can't have poles in the lower half plane. So this does have poles unless you actually suppress them. So you have to do something, and that gives you some constraints in the mathematics, which is great. But I won't use that version, but if I use this relationship here, then I can write phi minus is given explicitly in this term. Q has 2 unknowns, C and B are unknowns, so I need to suppress the poles in the lower half plane from the denominator. And this thing here has poles, and I can find them explicitly. They're very easy, and I call them beta 1 and beta 2, and there's plus and minus of those are these objects here. And I need these beta 1 and beta 2 to be real, so k squared must be bigger than this thing. So that's a constraint, just as I had before. So all I do is say, well, the numerator must vanish when the denominator vanishes, which gives me 2 conditions. I just substitute alpha as minus beta j in this thing. So I've got 2 conditions. And now I'll do the same for phi plus. If I take phi plus from this solution, do a lot of working out, you get the same thing, but now we have to suppress the poles at plus beta j, the 1 and 2, and so I get a similar equation. I get another 2 conditions. So normally in a Wiener-Hopf problem, you would find the right number of equations to solve for those unknowns that have come in through Liouville's theorem or through some other constraints, and then we have these. So I've got 4 conditions. Now I've got no forcing in the problem. So I've got no forcing, so there's no right-hand side. So if these are all linearly independent, then my solution will be 0. So I can't get it. So this is where, by forcing this, if I write it in matrix form for the 4 unknowns, I make the determinant of that vanish. So these are linearly dependent, then that will give me a non-trivial solution. Okay, it looks a mess, but it isn't. It's actually quite simple. It still doesn't look simple the way I've done it, but when I did it, it looked simple to me on paper. M plus of beta j, so this is m plus up the imaginary axis, because that beta is purely imaginary, works out to be a real constant for any value of the parameters, as long as your k is right, then you get something. I'll call it ej. It's just a number, a real number. X and big Y could be written in this form. So y is replacing k as my sort of unknown in some sense. But the betas also contain k as well. So implicitly, my eigenvalue k is wrapped up in all of these things. But if I write this thing here in this form, so I introduce aj and bj, then I get these quantities, and then I can write my matrix as a 4x4 system in terms of my unknowns is 0, and then I just have to set this equal to be 0, and then it can be done by hand. This is so simple, you get this relationship here. And I'm not going to show you very much or anything, just to say that, well, a couple of things. One, you can get zeros of this thing for a wide range of parameter values. And 2, does it reduce to the Konenkoff solution if the parameter Turin here goes to 0? It must do. So this is where I'm going to stop here. Preliminary results show that non-trivial, i.e. edge wave solutions, exist over a wide range of parameter values for which this vanishes. Because I've got so many parameters I can choose, so it's great. And also, it's not a function of the 4 independent parameters, k, nu, torr, and k, but torr over k appears paired together. So we've only got 3 really to play with. And I expect, and I've just done some very limited calculations, that these exist on ice and seawater. So I believe this is actually a phenomenon which one might be able to see if one took that simple model and believed it. Torr tends to 0, you can recover the Kanenkov solution. And it's much simpler than what I did in the past with Andy for a related problem for a compressible fluid. There was a very, very small window of parameter values which allowed these solutions to exist, but I think it's much bigger here. But I need to investigate characteristic wavelengths, frequencies, to see if there's a relationship between typical carving iceberg size and the typical K that one would see. That's me done. Thank you very much.
Time for questions, please.
Make one comment. You phrase this as an extension of Kanenkov's work, but based on my remarks earlier in the week, you'll know my impulse would be to say it's an extension of Tukachiva's solution, because it's exactly in the same framework, I believe. So it could be what you've done is the kind of most elegant extension of their analysis to the edge wave. So that's what I would think of it. But equally, it's both. It's a kind of intersection of 2 extensions.
It is, and your knowledge of the literature is far more extensive than mine, John, so I will definitely take your word for it. I agree.
Yeah, the formulae might come out related as well.
I think they will do, yeah.
Other questions?
Thanks a lot, though. I've got quite a few questions, but maybe some simple ones, like, have you computed like a physical, you haven't got as far as saying what physically it would be for some?
No, I haven't. I got distracted by other things. I did it on the aeroplane coming back from Australia, and then I did a bit more work. But no, I haven't actually put many numbers in, other than establish that there's lots of values of the parameters. Roughly, you know, it's hard in the literature to find out what the bending stiffness of ice is. For example, it varies greatly, doesn't it? And water, etc. So, but broadly speaking, yes, I've got those.
The limitations of a iceberg is not known. The Young's modulus is not known.
Yeah.
But the other one is there's another limit where the water's shallow, which is much easier.
Yeah.
And maybe for an ice shelf isn't so unrealistic because they're not in that deeper water and they're very long wavelengths.
Yeah, you're right. That's a good idea. I did it on infinite depth because it just was simpler. And I thought, well, at finite depth, you've got all those modes and stuff. It's more messy. But you're right. In the shallow wave approximation, well, I'm happy to look at you. I want to share it with you and Malta anyway, this work, and you'll know the literature better than I will. If we could do the shallow wave approximation, then that would be good to see the difference.
Just inspired by your comment in the very first slide, I understand that ice is important, but we can go to a very practical one. So you have a plastic wing in the water. So density is equal and stiffness is there. So it's exactly your case. Yeah. You should be able to observe that.
Absolutely.
And the Poisson ratio is half.
Yeah. Absolutely. So it does have applications in lots of those where you know the material parameters because you pick the material to use. So yeah, I think there are practical applications, and we know with water, it will drive these waves because you've got so much forcing onto the plate.
Yeah. Thanks for the really talk, Dave. We should talk more about this. Just one comment on the literature. Chikeva has done some more recent work on basically pressure patches traveling along the ice edges who iron juices. So I think that's another direction of
So I'm thinking of a sort of forced problem really, and you would need some localized forcing to set these waves going, and then they send the energy along. So there may be so.
I think like 2018, 19, we talked about that, right?
Okay.
Pilot just found.
Yeah.
Just quick question about it. Some at the beginning of the talk, you mentioned that you don't have capillarity effect. Is it to simplify the problem, or
Yeah.
at that scale they are irrelevant?
Yeah, so on this scale, capillary waves are irrelevant. One could put it in, but it just makes the math slightly more complicated, another parameter. But it's not necessary on those scales, absolutely.
Okay, let's thank Dave again for very interesting talk.